So, in the same way we have center of mass, we can talk about how it's moving. So, we can define the velocity of the center of mass as v cm for a system of mass as the weighted average of the velocities of the system. So, instead of looking at its position, we just kind of change it to velocities. This means how much mass is moving and in what direction. Now, we've seen that definition before secretly. And we'll get to it. Don't worry about it yet. What we're going to do is we're going to take the velocity center of mass, the idea speed of the whole system, and we're going to say that's made up of the fraction of the system mass for mass 1, and we're going to multiply it times that speed of that mass 1. And then we're going to add that to the fraction of the system of mass for mass 2 and multiply it times the speed of mass 2. And so on and so forth. We've seen this before. What's the fraction of a system of mass for mass 1? It's what over what? Kilograms over kilograms. We know the units. Mass 1 over mass total. That's the proportion of the total, right? Fraction of the system. Times V1. Plus M2 over M total, right? Same thing. Times V2 plus so on and so forth. Right? The fraction of the system of mass for mass 1 is mass 1 over mass total. Mass 1 is different than mass 2. Velocity 1 it could be different than velocity 2. What's the same? What can we factor out? Total. So 1 over total could be factored out. And so we have VCM equaling mass 1 velocity 1 plus mass 2 velocity 2 plus so on and so forth. Mass 3 velocity 3, mass 4 velocity 4, mass 5 velocity 5, whatever else happens. All over the mass total. What do you see in the numerator? I see something really fishy in the numerator that you should have kind of figured out. It's the formula for momentum. And so we're talking about how this means calculating how much the mass is moving. Wait, mass and velocity. And in what direction. So we're talking about the sum of all the momentum, P, of a system, divided by, and we're going to divide, to get the speed, we have to divide out the mass of the system. That's all we're really doing. Okay? So you have those parts. On this side of the equals, you have momentum over mass. On the far side, you have the speed that we're looking for. And so, if I was looking for, what would I typically be looking for? Momentum, right? You know this, that the momentum equation is that the sum of all the momentum of a system equals what times what? What's momentum? Yeah, the mass of the system times the general velocity of the center of mass, right? That's the symbol that we found. Velocity of the center of mass. The average motion of the center. times the mass of the whole system gives us the momentum of the whole system. That's not ridiculous. That makes sense. All that we know now is that we could find it in its parts, right? Alrighty, so let's look at a sample. A 5 kilogram sphere is moving east at 2 meters per second, while a 15 kilogram sphere is also moving east at 5 meters per second. What's the momentum for the system of spheres? They don't even have to collide. Maybe the faster one is in front and pulls away. We can still talk about the system, even though maybe one item is outrunning the other. You still have the same center of mass. You don't need the collision to happen. So how do we set up the math of it? What do we need first? I always start with my givens. M1, V1. Sometimes it's in my brain, but I always start with my givens. M1 is 5 kilograms. V1 is, what's the associated speed with that 5 kilogram object? 2 meters per second. Then we have M2. That is 15 kilograms. And the speed associated with that item is 5 meters per second. Good. What is the momentum for the system of spheres? We know that the net momentum equals M1 V1 plus M2 V2. Even without colliding. That we've got 5 times 2 plus 15 times 5. 10 plus 75. 10 plus 75 is 85. And both of those numbers are positive. So the positive for us is east. 85 kilograms meters per second is the unit. And that's my net momentum. Does that answer the question? What is the momentum for the system of spheres? Okay. What is the velocity for the center of mass, though? How would you find the velocity? Momentum over mass. All right. Now, you could see that this numerator was really M1 V1 plus M2 V2. But you might just write down 85. And what's the mass of the system? Yeah, I have 5 plus 15. Um, 4 1/4. 4.25 meters per second. That's how fast. Ooh. Yes, that's how velocity it's going. I changed it from how fast to what velocity. All right. They give us the same numbers, 5 and 2, 15 and 5, but it's east and west. So the momentum for the system of spheres, similar idea, similar problem, same givens, except one of them's a directional difference. The momentum equals M1 V1 plus M2 V2. Start with your equation. But it's 5 times 2 plus 15 times what? Negative 5. So I've got negative 75 and 10. When I add these together, my net momentum equals 65. Right, so negative east is west. And in the units, it's kilograms meters per second is what I was also trying to fill out at that moment. when I paused and waited for more information. What is the velocities for the center of mass of the system? What is the velocities for the center of mass for the system? We just do the same thing, right? Except instead, this is negative 65 in the numerator and 5 plus 15 in the denominator. We're doing VCM equals the momentum divided by the mass. We're dividing by the same 20. So it goes in 1, 2, 3 and a quarter. 3.25. It's got a negative sign in front of it. So what direction is it in the end? West. So that 3.25 meters per second west. Okay. Last part. Recall the impulse momentum theorem formula. What is it? J equals, that's impulse equals change in momentum. Change in momentum in Newton's law is what times what? Force times time. Okay. We can apply this to a system of masses. If I have the force external, if I look at all of the forces that are acting on the system from outside of the system, times the time, that's the change in momentum, right? What else does that equal? What's another way of saying triangle P? Right, if we have two items that works, I could just say it's the masses in general times the change in velocity. Divide both sides by time. This side and that far side. If I divide by time, I get force external equals m delta v divided by t. What simplifies? What's velocity over time? What's change in velocity over time? You're telling me that all of this is just F equals ma. So what are we talking about now, though? We're talking about any force acting from outside the system on the system will accelerate the center of mass, right? So now we're talking generalities. If there was some outside gravity spread across the entirety of all of your molecules, not just like your heart, not just your hand, then you'd move together and accelerate in that direction. So a net external force, such as gravity, applied to a system would result in a uniform acceleration of the system, of all the system. You could try to counteract it, but this is like when you're falling and you are on a piece of debris and you try to jump off the piece of the debris, you're gonna have to kick it down extra hard to slow your fall at any small bit. An object falls and blows up. The center mass of the system would continue to fall and accelerate. As if nothing ever happens because all of the various pieces are experiencing the same acceleration. But this is also helpful because we talked about frame of reference, right? And we talked about filming in a big plane, right? Things like that.